think it's 10:30. It's time to begin. Hello, everyone, and welcome to today's webinar on applications of machine learning in battery research. My name is Kiana Amini, and I'm the president of the Waterloo Electrochemical Society Student Chapter, or WatECS. WatECS is a branch of the International Electrochemical Society at University of Waterloo. Our goal is to create a community of scholars by bringing students, faculty members, researchers in universities all around the world together and connect them to those who are working in industry and different countries, in different companies in the field of electrochemistry and solid-state sciences and technology. So we organize seminars and webinars, events, meetings, conferences throughout the year for the benefit of our community. Before I introduce our presenter today, I would like to go over a few items. First of all, this webinar is being recorded, and the recorded webinar will be available on our social media after the presentation. I'd like to encourage everyone to share this webinar with your social media so that if anyone couldn't attend today, they still have access to the webinar. Also, at the end of this presentation, and I believe that in the middle of this presentation, we have, in fact, 2 Q&A time where you can write your questions in the Q&A box. The Q&A box should be on the bottom right of your screen. If it's not already there, at the bottom of your screen, there you can see an icon with 3 dots. If you click on that, you can choose a Q&A box and write your questions there. Also, for students who are attending from Chemical Engineering Department at University of Waterloo, towards the end of this seminar, I'm going to share a code in the chat box that you can use that to get credit for your attendance. Okay, now that I've covered these points, I'm pleased to introduce today's speaker, Dr. Kristen Severson. Dr. Kristen Severson is a postdoctoral researcher at IBM Research in Cambridge, Massachusetts. Her interests are broadly in applied machine learning with a current focus on healthcare applications. Prior to joining IBM, Kristen earned her PhD at MIT, where she worked on machine learning applied to problems in lithium-ion batteries, production oil wells, and bioinformatics. She also holds a bachelor's degree from Carnegie Mellon University. Now, without any further ado, we will turn time to Kristen.
Thanks, Kiana, so much for having me and the University of Waterloo. I'm excited today to share some of our work in applying machine research into batteries. In addition to sharing results today, I hope to do a little bit of tutorial on some of the machine learning techniques that we used in this research, such that you might be able to apply some of these ideas to your own work. So the particular application I'll be talking about today is extreme fast charging. And specifically what we mean with extreme fast charging is going from 0 to 80% state of charge in only 10 minutes. So the idea here is that if electric vehicles, for instance, were able to refuel faster, there would be much more broad adoption of this technology. And there's a hypothesis in the literature that doing multiple steps of charging could lead to improved performance. And the trade-off that we're working against is generally you can charge a battery very quickly, but then you see a degradation in its lifetime. So our goal is how might we be able to charge these batteries very quickly without seeing large losses in terms of the battery lifetime. So you might be asking, why aren't we already able to do this type of analysis? And there are a few challenges with current approaches. The first of which is unoptimized empirical testing. As we consider more and more complex charging protocols, the parameter space increases, and doing a simple brute force approach ends up having combinatorial complexity as you're increasing the complexity of the charging protocols. We might also think that we could leverage first principles models. However, the current state of the art isn't a systems level optimization, which we would need in this application. And lastly, in the past, there's been really only a limited amount of data analysis, leveraging summary relationships to model trajectories. I do think that this is a trend we're seeing changing currently as more interest is growing in applying machine learning, as well as growing data sets in this area of research. So today I'll be talking about our closed loop testing and optimization approach, which really has three components: a high throughput experimentation platform, an early outcome predictor, and a Bayesian optimization technique for design of experiments. I'll go through each of these three pieces in more detail, starting with the experimental platform. So as I mentioned, this experimental platform uses high throughput cycling. Specifically, we tested commercial lithium iron phosphate graphite cells. And during each charge and discharge cycle, the platform's able to measure temperature, internal resistance, current, voltage, and capacity. This setup allows 48 batteries to be cycled simultaneously. And this gave us an initial data set of approximately 96,700 cycles. Now, if you're coming from a machine learning background, that perhaps doesn't seem like a very large data set, but I think if you're coming from material science or electrochemistry background, you know that this is quite a large amount of data. And at the time we published the data set, to the best of our knowledge, it is the largest available data set. The experimental setup is shown here on the left, and I think this is a good time to point out that I am not a material scientist by training, and all of the physical experiments that I'll talk about today were run by my collaborators pictured here. And from left to right, this is Nick Perkins, Peter Atiyah, and Norman and Jin, who are current and former Chu lab at Stanford. And so the first piece of analysis I'll talk about then is our early outcome predictor. And this is the piece of the work that I led. So the metric of interest that we wanted to predict was cycle life. So lithium-ion batteries come with some nominal discharge capacity that's shown to degrade over time. And time here we'll actually measure in terms of cycles, which is a charge and discharge event. The cycle life of the battery is the number of cycles that are required to reach 80% of the nominal capacity. So here I'm showing the trajectory of several of the batteries we tested, and the cycle life is the point at which the trajectory crosses the x-axis. In this case, these batteries have a nominal capacity of 1.1. And so you can see some diversity in these trends. At this point, once we cross on this x-axis and reach this 80% nominal capacity, we consider the battery to be dead. So the goal of this piece of work is to accurately predict the cycle life without observing the full trajectory. And not observing the full trajectory is pretty highly motivated because it can really decrease the amount of time it takes to run the experiment. Particularly as the chemistry of these batteries improves, the cycle life continues to extend, and it takes longer and longer to understand how changing the way the battery is operated affects its cycle life. And so you might be thinking, well, this problem isn't particularly difficult. We'll just run the battery a couple of cycles. We'll correlate the discharge capacity after those cycles with the lifetime, and the problem is solved. But what we see is that discharge capacity, even after 100 cycles, which I'm showing in the plot here on the right, is not cycle life. We see just kind of a wide grouping, and this model isn't accurate enough, or this simple type of model isn't accurate enough to meet our cycle life prediction task goals. So instead, what we proposed is that we can engineer features which can be correlated to cycle life. So in a machine learning context, a feature simply means a mathematical transformation of our observed data. And so the particular types of features we were interested in have to do with the voltage capacity curves. So I'm showing these two curves corresponding to cycle 10 and cycle 100 on the right. And each dot on our capacity fade curve, two of which I'm showing here on the left, have a corresponding discharge capacity voltage curve. And we can see that that curve is changing with cycle number. So the hypothesis will was that we can generate features based on these curves and correlate them to the eventual cycle life. And so here are some of the features we ended up considering. On the left, again, we have this voltage capacity curve. We considered the difference of these as a function of voltage, which I'm showing in the middle plot here. Now, each of these trajectories is correlated with the eventual cycle life of the battery, and we can begin to see some pattern. We are interested in summarizing these trajectories to be then fed into our model. So on the right, I'm now showing the variance of the difference of these curves. And what we found was once you've done this transformation, there's a high correlation between this new feature and cycle life, such that it is suited for our modeling purposes. Now, this was a great result, but you might ask, well, why this feature? Can we propose other features and see what the results are? And that's where the machine learning comes in. So I want to introduce feature selection as a machine learning problem, and I'd like to start with a quick review of linear regression. So this is a very simple type of model where we have some factors that we've measured, x1 through xd for a sample xi, and we'd like to predict some outcome given a linear combination of those measurements. We can see this visually in a simple one-dimensional case where we've measured some x's and we have some outputs y. And we want to fit some line to serve as a predictor, and we're going to fit that line by minimizing the error of our observed data from the prediction, which is shown by these vertical lines here. We can formalize this mathematically in terms of an optimization problem, where now we're looking for the values of our coefficients W that minimize our loss, which in this case is going to be the squared error of our observed data versus our prediction. So this is a simple ordinary least squares. You're likely already familiar with this technique. What this doesn't achieve is our goal of the feature selection problem. So now, instead of fitting all of these coefficients, W1 through WD, we'd like to learn some subset. So to select a subset, we might consider some kind of budget for the coefficient, for the number of coefficients in our model. And we could propose this optimization problem as I'm showing here, where now we've added a penalty, which is an L0 norm, which simply counts the number of non-zero elements in our coefficient vector. This would certainly achieve the goals that we've specified, but unfortunately, this is a non-convex formulation, which we would typically solve by enumeration. And this combinatorial complexity means that it's infeasible even for relatively small problems. So what we can consider instead is how we might relax that constraint. So now I'm showing the problem, but in terms of the weight space. So let's say we're trying to learn two coefficients, W1 and W2. Our optimization is again minimizing some loss, which in this case is the squared error. And I'm going to indicate the best solution we would have found without any type of constraint with this black dot here. Then we have the contours optimization as we move away from the best solution. Again, this is the solution, this black dot, that we would find if we solve the ordinary least squares problem. Now, if we add our L0 or our zero norm penalty that we talked about in the previous slide, we could imagine a version of that where we say, okay, we can have like one coefficient. So we have these solutions here indicated by the blue circles. But we already said that that had combinatorial complexity. So what we can consider instead is the convex relaxation of that constraint. And so now for our budget, we say we can have any set of coefficients that falls inside this box. And this is a well-known technique referred to as a lasso. So now instead of that zero norm penalty, we have one norm. And the one norm is the sum of the absolute values of the coefficients. And what we find is that geometry generally encourages sparse solutions. So here, when we look at where our constraint intersects our optimization, or the contours of our ordinary least squares optimization, we can see that the value for W1 is actually 0. So this will achieve our goal of learning a subset of our coefficients. Now, in practice, what we ended up using for this study is a slight modification of this optimization framework known as an elastic net, where here we're considering a convex combination of two penalties, a one norm and a two norm. And the difference of doing this versus the lasso technique is there's an additional penalty, which kind of rounds out our constraint in a geometric sense. But what this provides us is, in the event we have highly correlated predictors, so let's say our measurements, some of them are highly correlated, we can have a degenerate solution in the lasso case where we would have switching behavior. The model will arbitrarily pick one or the other of those correlated measurements. But we think that having correlated measurements could be valuable when working in these applications because you might have some robustness against measurement noise by leveraging these different combinations of those different physical measurements. And so we use this elastic net approach as our final learning tool, such that we can both perform the subset selection goal as well as possibly include correlated measurements for our prediction model. Okay, so returning back to the application, what we needed to do was propose a series of these transformations, again called features, of the raw data that we think might be predictive of cycle life, and then apply the lasso algorithm to learn some subset. In doing this, we considered increasing complexity of features based on data availability. So I mentioned that our high throughput platform could measure many things like capacity and voltage, but also temperature and internal resistance. So we wanted to consider scenarios where perhaps you wouldn't have access to features like temperature or internal resistance. Now, in doing this, we divided the data set into training and testing sets. This is a very standard thing, but I want to take some time to emphasize doing this. All it is simply taking our data set and partitioning it into some data we're going to use to learn the model and some data we're going to use to test the model. I find in science applications, oftentimes you don't have access to very much data, so there's an interest in using all of your data to train the model. And I would caution against this, particularly as you start using more and more advanced machine learning tools, because these are very flexible and powerful models, and they might simply model spurious correlations in your data and not generalize well. And by generalize, I mean apply to data that wasn't used to train your model. So I want to encourage this. And in this analysis, we were actually able to go a step further because we had a third data set, which was generated after our training and testing data. So this is an even stronger measure of generalizability because the experimental conditions change slightly as you run more and more tests. So here are some of the results. From left to right, the models are of increasing complexity, where again, I ranked them based on the amount of data you need to apply them. The leftmost plot is the single feature only model. That's leveraging only the variance of the change of the capacity as a function of voltage curve that I showed previously. And we see using only that measure, we're actually able to perform rather well. These plots are showing the observed cycle life as compared to the predicted cycle life. So the diagonal line would be points which have no error. We've also included this dotted black line here, which is the 100 cycle, the point at which we've observed 100 cycles. And this is just to serve as a reminder that this is how much data we observe before we make the prediction. So these batteries do have significantly more cycle life than the point at which we're making our predictions. And we can see that as including additional features learned by the model, we are able to improve the result up to 9% test error in our best model. So one of the things that can be exciting when you use engineered features in a machine learning framework is the potential to interpret the result. And this is because we know exactly what mathematical transformation was applied to the observed data to drive the predictive performance of our model. And so in an effort we at this point in our work knew that these voltage-based features performed well, but we wanted to be able to tie that back to the degradation mode of the battery. And in order to do that, additional experiments were run with some slow cycling conditions. Slow cycling gives us better insight into the degradation modes. So the specific analysis that was run is a differential capacity analysis, and I'm showing one of those results here on the left. In the literature for these LFP graphite cells, the differential capacity has been mapped to different degradation modes. So we can look at shifts in these curves and relate them to the likely source of degradation. In this case, the shifts indicate that the loss of active material in the negative electrode graphite was the primary degradation mode. And so this was a somewhat exciting result because we think that this degradation mode can be rationalized in terms of why voltage features were predicted. So specifically, when these cells are manufactured, they're typically manufactured with more graphite sites than lithium ions. And as this LAM mode is happening, the number of sites is decreasing. And that changes the crystallographic ordering of the lithium ions in the graphite. And how that manifests is in the voltage, but not in the capacity. So this result helps us rationalize why these voltage features would be predictive, but we wouldn't see this manifest in that overall capacity fade curve I showed at the beginning of this section. So this is kind of a nice result that we are able to use machine learning to do a prediction and then take the results of that machine learning model and go back and interpret them in a materials research context. So that section is on the early outcome predictor. This is where I was planning to pause to answer some of the questions about this part of the analysis. So Kiana, I don't know if it's better for you to ask them or I can look back at the Q&A.
Sure, I can read it for you if you want. We already have, I think, 7 questions, but stop me when you want to continue for the rest of your presentation.
Sure.
So the first question asked, how would you be using machine learning for battery packs while the vehicles are in use?
Yeah, that's a great question that I frankly don't feel I have a great answer to. I'm not necessarily an expert in how these batteries are used in driving applications, but I think with the right instrumentation to capture data, there are certainly opportunities for onboard machine learning applications.
So the second question, what were the boundary conditions for testing of cells from charging to discharging? Was it uniform or was it varied from cell to cell?
In the data set we leveraged for the early outcome predictor, we are varying the charging protocols used. And we think that that helps kind of excite a response in terms of the distribution we see in the cycle life of those batteries. So those are nominally identical cells run under different conditions to get a wide range of cycle lives.
The third question, how are the chosen features related to the underlying charge-discharge dynamics of the battery? In other words, is there any relation between the features and the cell parameters?
Right. So hopefully that question was answered by our interpretation in terms of the degradation method being the loss of active material in graphite. That was really the core of our interpretation of the feature. Perhaps whoever asked that question could ask a follow-up if that interpretation didn't make sense.
The fourth question, what is the lasso method? Lasso.
Yeah, the lasso is a technique used to simultaneously fit a model, a linear model, as well as learn a subset of the coefficients of that model. So it's an algorithm.
The fifth question, what are the constraints that need to be considered when thinking about deploying a machine learning model in real-time battery management systems? How important is inference speed and memory space requirement for things like state of charge or state of health estimation tasks?
Right, so we only really looked at state of health, and I'm not confident how state of charge modeling would go. Certainly in our case, most of the computational effort is in learning the model, and then it's just a linear model in the end. So if you have the instrumentation to get the data, it's very easy to apply. And I think that's really going to vary based on the application.
Mm-hmm. The sixth question, do you think more testing and channels is always better, or is there a sweet spot for testing a new cell?
I mean, eventually, hopefully you have a robust enough estimator that you don't feel you're going to get information from additional experimentation. And we'll talk a little bit about that in the next part in terms of a design of experiments context. But I think sample complexity is always an important question in machine learning.
Seventh question, loss of active material in graphite electrode is meaning that the delamination of electrode materials. I'm not sure if that's a question. I move on to the next one. Why did you try to reduce the number of features? It seems that even if you took all the potential features, the computing cost wouldn't be high.
Right, that is true. In this case, we could have taken all the features, but here we expect that some are poor estimators because we're going to propose kind of a wide variety, some of which may not really be correlated with cycle life. So that also motivates the subset selection.
Ninth question, LFP material is known to be very stable, so degradation can be neglected. Do you think that lifetime can be predicted using ML for other cathode materials like NMC besides LFP?
Yeah, that's a great question. I hope so. I hope that, maybe these features wouldn't be appropriate for other chemistries because the degradation modes would be very different. But I think that there's a lot of opportunity to do this type of analysis in other chemistries.
How can we request a modeling code academic license? What's the procedure?
You should reach out to my advisor, Richard Bratz. It's bratz@mit.edu. His information is on the final slide of the presentation.
Okay. Do you still have time for more, or?
Yeah, I think maybe we'll do questions until 11, and then I'll start so maybe 3 more minutes.
Okay.
Yeah.
Why your model performs better, mean percentage error, on the secondary test data set than the training data set?
Oh, I mean, I don't have a rigorous answer to that. It could be a function of which charging protocols we used. We also had a battery in the training data set that had kind of suspicious behavior that might have failed under a different mechanism than most, which really drove higher error as being an outlier in terms of its expected lifetime versus its observed lifetime.
In your opinion, computational intelligence, for example, genetic algorithm, is a subset of AI, or is it a category of its own?
For me, the field, the ML or AI field is evolving so quickly, and there's so much growing interest that I generally think it's probably good not to try too hard to partition it neatly. I think we're still learning a lot about the way different algorithms are related to each other. So I would think of it maybe more as an evolving toolbox than worry about some kind of hierarchy.
Is there an optimal size for the training data?
Yeah, that's a great question. That goes back to like a sample complexity question, whereas how much data do you need to learn the model? And I don't have a rigorous answer to that at this point. I think we found value in having at least some amount of diversity in the cycle life. That was very important. So I think in some ways it's not only a question of the number of samples, but what kind of, how have you covered the space that you're interested in modeling? So unfortunately, I don't have like a succinct or rigorous answer to that question.
I think we also have a question in chat. Please ask your questions in the Q&A box, but I read this one from the chat. Can we model and predict the temperature dissipation and thermal management using the artificial intelligence modeling?
Potentially. That's not a question, that's not a task that I personally have attempted to do, but I think looking at all sorts of different outcomes and predictions is interesting in this space.
Mm-hmm. Is there an optimal, which features did you use for the machine learning?
Yeah, we used a combination of those transformations of the capacity voltage curves, as well as features related to capacity fade and temperature modeling. For the exact details of each of the features, I would suggest looking at the paper.
Okay, I think it's 11. I think we covered most of the questions.
Great. Okay, well, let me continue then. So that the next step of the analysis was to look at Bayesian optimization for experimental design. So as I mentioned at the top of the talk, our interest was in learning charging protocols such that we can achieve fast charging without large loss in terms of cycle life. And so I'll get into how that was done. And so now in this section of the talk, the parameter of interest is the charging protocol. And as I already mentioned, fast charging is desirable as we hope it would increase adoption of electric vehicles. But we also often see this trade-off. So there's a hypothesis in the literature to use multi-step charging, where right now it's just a constant current and then constant voltage steps to charge a battery, but perhaps varying levels of constant current could improve our ability to charge quickly without this battery loss. So the particular charging protocols that were investigated have 6 steps. The first 3 are free within these ranges denoted by the pink shaded regions. And then the 4th step is constrained such that the total time here is 10 minutes. That's to go from the 0 to 80% state of charge, followed by a last constant current and constant voltage step. So here in red and then in blue is an example of one possible charging protocol that could be tested. So in classic experimental design, the control variables are carefully chosen, and then you're going to search that space in a way such that you can look at the relationship to get a diverse set of experiments. So perhaps you're already familiar with experimental design methods such as factorial design. In Bayesian experimental design, a surrogate model of the observations is used to help you choose which experiments to run. So I want to provide an overview of what Bayesian or optimal experimental design looks like in just a general context. So you have some design space, which are the variables you're going to control, in our case, charging protocols, and the experimental result you're interested in, which I'll denote Y, which in our case is the cycle life. So to start the optimal experimental design procedure, you're going to run some random subset of the possible design space and generate some data sets. So now we have pairs of experiments and outcomes. Then you're going to leverage that data to train a surrogate model, which takes in the experimental conditions and estimates the outcomes. Using this model, we can calculate an acquisition function. The acquisition function serves to assess the utility of a particular experiment. We can then optimize that acquisition function to select which experiments we'll run, and then run the experiments. At this point, once we run the experiments, we can augment our data set and retrain our surrogate model. And we'll repeat this procedure until either we're happy with the experimental result or we've exhausted whatever experimentation budget we have access to. So there are really 2 key ingredients to be able to use this optimal experimental design platform, and those are a surrogate model and an acquisition function. So the surrogate model in our case needs to predict cycle life as a function of charging protocol. Now, of course, if we had a rigorous model that mapped charging protocols to cycle life, we would already be done because that's our goal, to choose the charging protocol that leads to the best cycle life. So instead, we're going to consider how we can encode our uncertainty in this function by using different probabilistic measures. So what we'll do is we'll specify a likelihood of the cycle life, Y, as a function of our charging protocols X and some parameters theta. So really what we're hoping to leverage here is the smoothness of the space. Basically, if we have two very similar charging protocols, we don't expect them to have very large deviations. And we're going to use this fact to help guide our experimentation. Now, we still need to have values for theta, so we can encode our uncertainty in theta by using a prior. In this work, an isotropic Gaussian prior was used, which means it has a zero mean and diagonal variance, meaning that the coefficients are uncorrelated. Then as we observe data, we can update our belief about the distribution of these parameters, which is called the posterior. I'm showing the specific update equations here, but really all I want you to take away from this is that the updates are a function of our observed data, X and Y, at our iteration T. So I want to just quickly show this graphically to give a sense of what we're doing. So we'll take a simple example where we're just looking to learn some intercept and some slope for univariate theta. Our prior is shown in terms of contours here on the left, and you can see that it's just evenly distributed with no correlations. And if we consider which linear models could be possible under this distribution of parameters, we see all of these red lines here. So effectively at the outset of our experimentation, we see any model is possible under our current belief about the parameters. Then we start observing data. So here I'm showing you the data point as a blue dot. I hope you can see it on your screen. So now some of the models that were previously appropriate under our uncertainty of our parameters are no longer appropriate because they don't model the observation well. And we can see that manifest in our new belief about the distribution of the parameters shown here in the heat map. So now there are some values of the parameters that are very unlikely given the data we observed. As we keep observing data, our uncertainty about the parameters decreases. So now that we have 2 points, there are again some models that don't fit our data well. And as we observe more and more data, we become more and more certain about the parameters. Now I said we needed the 2 ingredients. The second ingredient is the acquisition function. And what the acquisition function is doing is telling us what's the utility of another experiment. And the way we're going to judge the acquisition function is by looking at the posterior predictive distribution, which says what's the probability in our case of the cycle life given certain experimental conditions marginalized over our uncertainty in the parameters. And that's this equation here. And so the particular functional form that was applied is the upper confidence bound. And the upper confidence bound looks at 2 factors of this distribution, the mean and the variance. So the mean can be mapped to what's often referred to as exploitation. So the mean tells us what do we think the cycle life is going to be. We want that to be as large as possible. So as we get information about successful experimental conditions, we are likely to be interested in running charging protocols similar to that successful charging protocol. But we also need to take into account that we're relatively uncertain about how to model cycle life as a function of charging protocol. So we also want to have this exploration piece, which is related to the variance of the distribution and is a measure of our uncertainty. So we're trading off these 2 forces, exploration and exploitation, in deciding which experiments to run next. So I want to quickly return to the flow diagram of the optimal experimental design and point out again that now our design space is charging protocols, our experimental result is cycle life. And the first piece of the talk about early cycle prediction is actually going to come into play in this step where we would typically acquire new data. So instead of cycling the batteries to failure, we'll use the early prediction model to speed up our experimental time. So 100 cycles of the battery will be run, then we'll make a prediction about how long the cycle life will be and use that to train our surrogate model, which maps charging protocol to cycle life. So there are 2 predictive models being used here. Okay, so let's return to the application. Again, we have this space of constant current steps that we're looking to investigate. And we can also reconsider this now in terms of 3-dimensional space, where we have the 3 constant current steps, and then the fixed 4th step, which is just indicated by the color here. That space was discretized such that there are 224 charging protocols that we are interested in testing. Okay, so now we can see kind of how this looks in action. The first batch is just a random sample over those 224 charging protocols. And we can see the predicted cycle life versus that design space here in the plot. Based on this result, new experiments are proposed. And you can kind of see the manifestation of that exploration and exploitation trade-off. There were some good protocols occurring in this region, so we see many tests there. But there also was this region here that wasn't really tested in batch one, so there are also some protocols in that space that were tested. And then as we continue, you see a concentration in the space that's well-performing until the batches are completed. I should have mentioned in this context, it was proposed to do a fixed budget approach. So you're going to keep running experiments until you've exhausted your budget. Just reiterating the exploration and exploitation trade-offs, 67% of the batteries that were tested actually only test 21% of the protocols. So because of our smoothness assumption, there are various aspects of the space we don't need to test, and we can still have pretty high confidence that we found the best or near optimal charging protocol. We can also look at how this evolved in terms of our parameters. So here's the space of parameters that maps the charging protocol to the cycle life. And you can see that initially everything is uniform. So we have really no expectation about how the charging protocol maps to cycle life. But as the experiments are run, we start to see that some regions are likely to have high cycle life. So these results were validated using a couple of techniques. First, this here is just showing the number of repetitions for the protocols. And again, reiterating that many protocols are not tested by using this optimal experimental design protocol. In fact, there's less than one cell per protocol in the end. Then the validation experiments were run using the charging protocols that were identified optimal experimental design procedure, and those were benchmarked against literature-inspired and other charging protocols. This plot here on the right is showing the true ranking of how these charging protocols mapped to cycle life versus our expectation of the ranking. And so what's important to see here is you can see that the optimal experimental design protocols were in fact better than the ones observed, the other ones tested and benchmarked against. So overall, this procedure was able to assess 224 charging protocols in only 16 days versus the brute force approach, which would have taken approximately 560 days. So this whole pipeline really enabled a great speed up in the analysis. So just like before with the early prediction, we might be interested in what can we learn about the physical system by interpreting the machine learning results. So first here on the left, I'm showing the optimal charging protocol that was selected by the model in red and then blue. And what you can see is that it's actually relatively flat. Now, the literature would suggest monotonically decreasing constant current steps, which would be optimizing for lithium plating in terms of designing these protocols. So this is somewhat counterintuitive of a result, but analysis was performed to hypothesize why or rationalize this result. And here is a look at the sum of the constant current steps plotted against what the OED estimates cycle life to be. And we can see a pretty good correlation, which my collaborators hypothesized that perhaps this is optimizing for heat generation in choosing this very flat charging protocol. This result is still being investigated, but it's at least some evidence that perhaps heat generation is what's being optimized for in this particular charging protocol. Oh, and my collaborator thinks it's definitely not optimizing for plating, whether or not it might be heat. So today's presentation is really based on two recent publications that I'd like to highlight. If you're interested in learning more, those are shown here. And I'd also like to encourage everyone to try some of this themselves. I think I mentioned already that there are so many opportunities for machine learning in battery or materials research. And to get started, our battery dataset is available. I've included the link here. There are a lot of open source machine learning packages. For instance, you can use scikit-learn to implement tools like the Lasso or ElasticNet, or GPy is an open source toolkit to do Gaussian processes, which is how that Bayesian optimal experimental design algorithm was deployed. There are lots of open access machine learning courses on edX, Coursera, and YouTube. And I also recommend, in particular, these two books, Pattern Recognition and Machine Learning by Chris Bishop, and Machine Learning: A Probabilistic Perspective by Kevin Murphy. I believe both of these books are available online. I'd also like to make some important acknowledgements. So all the work that I showed today, for my part, was done while I was at MIT, and a member of Richard Bratz's group. This is who I was referencing, can give you access to the prediction code if you're interested in it. It's only available under an academic license, but his email is just his last name, Bratz, at mit.edu. Also like to acknowledge Will Chu's lab at Stanford. They, again, did all of the physical experimentation. And Stefano Arman and his grad student, Aditya Grover, also at Stanford, they led the Bayesian optimal experimental design aspects of this work. And I'd like to re-acknowledge the experimentalists Nick Perkins, Peter Attia, and Norman Jin. In particular, Peter, he really was a constant thread throughout all of these pieces of work, and also helped make these slides. I'm so very grateful to Peter. Finally, funding support for this work was provided by the Toyota Research Institute. Also like to acknowledge them. And with that, I'm happy to take additional questions.
Thank you so much, Kristen. We had one question from the previous section of your presentation that I missed. The question asks that in the data set you showed, it seems like the predicted behavior fits well the data for small number of charge cycles. However, when increasing the number of cycles, it seems that there is a small change to a non-linear behavior. Has this been
Yeah,
studied?
that's a great observation. My personal opinion on that is that there were some calendar aging effects at play that we didn't fully account for, and those are really more related to the particular batch of batteries than the lifetime. But we didn't, I think the model was deemed to be fit for purpose, and we didn't specifically investigate that aspect of it.
Also, we have a question. I think it refers to the earlier question that asked for achieving the code, for getting the code. You said they should email your supervisor, PhD supervisor. Someone is asking if they should email directly Dr. Bratz or someone else.
Yes, no,
Dr.
yeah, direct to Bratz.
Okay, as you took only discharge versus voltage for some fixed values of temperature, resistance, would you say that you might be studying only some linear behavior?
Oh, I'm sorry, I don't understand that question.
Yeah.
Maybe that person can
Yes.
ask.
Yes. Okay, so I would go, what are the software used for modeling? And Lasso algorithm, is it open source? And is there any database available which can be used for machine learning?
Yeah, so the analysis that was done was performed in MATLAB. There's not necessarily any reason you couldn't also use Python. I'm not sure of other tools, like if there's probably an R implementation as well. I'm just not as familiar with it. And the data set is available, if that's what you meant by the database. But there are many tools. I highlighted the open source ones here just in case you don't have a MATLAB license. Both can be successful.
How did you get the intuition that Q100, Q10 feature was a useful feature? Trial and error or something else?
Yeah, a lot of it was based on my experience in applying machine learning techniques, kind of taking inspiration from work I had done in production oil wells. So my collaborators had been considering a dynamic time warping technique to remap capacity to a fixed length, basically transform that space so that it would always be in the same range of capacity. And my hypothesis was that we could instead kind of capture the change in that and correlate it to cycle life as opposed to trying to make that consistent.
Mm.
So I think it really born out of my experience.
Can you use this approach for predicting faults such as short circuits or thermal runaway in batteries?
That's an interesting question. So typically when I think of like a fault identification problem, I'm thinking more of like a one class classification where you're looking for deviations from normal behavior. So I don't know that this model is well posed to do that, but I do think that you likely have the data you would need to learn something like that. My suggestion would be that you're looking to characterize normal operation and then learn some measure that captures deviation from that to do that type of fault identification problem. I guess, and sorry, going back to the last question, I should mention that we did do some more rigorous testing around those particular indices, the fact that we used 110, and we didn't see like any particular spike that led us to think that like it's very brittle, but 110 are kind of useful numbers. The idea that we were going to run 100 cycles is just nice round result.
Could the DVDQ be useful for state of charge estimation as well? How dependent is the importance of this feature on battery chemistry?
Yeah, that's a great question that I think goes back to the earlier question about NMC batteries. And without doing experiments, I don't really know. It might be useful, or maybe some related concept would be useful, but I think it's difficult to say a priori.
Your 2019 publication in Nature Energy gives a nice review of part one of this presentation. Are you planning a second publication regarding the optimal experimental design for determining the best charging protocol?
That's this paper, which was published in Nature here, closed loop optimization of fast charging protocols for batteries with machine learning, led by Peter and Aditya.
Okay, can you give some details about the selection of input of this model? When you choose them, how can you know that the input you selected is the best to predict the output, in this case, cycle life?
That's what we're relying on the lasso algorithm, or in fact, specifically the elastic net algorithm to do for us. And so we're just going to hypothesize a large number of features that we think could be predictive and let the machine learning approach determine that subset for us.
When you applied the lasso to the cycle life prediction, did you use any method to smooth the noise of the training data and test data? If yes, what kind of method you use?
We did do a linear interpolation of those voltage capacity curves such that they were sampled at a consistent step in voltage. The details of that are available with the data set. I'm not recalling them offhand. And then there was some kind of analysis looking for what I would call like gross errors in the capacity. So if we saw like very, very large jumps, we went ahead and threw that data away because we are relatively confident that that's not a physical, that's a measurement noise.
Was the objective of the Bayesian GOE to find the most accurate prediction of cycle life or to find the optimal fast charge protocol?
It's to find the optimal fast charging protocol.
If the best charging protocol is pretty flat, does it mean that it's actually not better to have a multi-step charging protocol? Seems almost like a single-step charge.
Right, that's a great question that I don't know the answer to just because of my expertise not really being in this space. But I do think that's a really interesting question.
Questions on part one. So this is related to the part one of your presentation. Why use engineered features and a regularization like lasso, elastic net versus passing the whole voltage profile for cycle 10, cycle 100 through a neural network? or similar that could be more flexible? Is it just for interpretability?
Right. I think that's what really drove our analysis, the interpretability. I think that, given this early result, because, at the outset of this, I don't think we were necessarily so confident it would work. So having something simple is valuable, but given the early success of this, I think considering more complex neural network architectures is an exciting direction.
Were the best protocols found by ML coherent with experimental expectations?
Oh, sorry, Kiana, can you say it again?
Sure. Were the best protocols found by ML coherent with the experimental expectations?
I would say no, and that relates back to that idea that the multi-step charging protocols are typically monotonically decreasing in constant current, with a thought that would optimize against plating, and that's not what the optimal experimental design found, and that was validated in additional experimentation that the optimal experimental design identified protocols did perform well.
I missed this question out last time. Could the DVDQ be useful for SOC estimation as well? I guess I asked this question. How dependent is the importance of this feature on battery chemistry?
Right. I think we've kind of touched on this one, and the question I think probably goes back to what are the degradation modes of the different chemistries. So we really think the predictive power of the feature is related to the fact that the degradation mode is the loss of active material in the negative electrode, delithiated negative electrode to be specific. So if that is also the degradation mode for other chemistries, we have at least some reason to believe that the feature would be predictive.
So next question. Okay, someone is asking if they can reach out to you for further questions.
Sure. And my email is my first name dot my last name at ibm.com. And that information is also available online.
Please specify machine learning models or alternatives for sizing of batteries for battery energy storage.
Well, I'm not sure I can answer that question without a lot more detail.
Was there any effect, or would there be any effect on the results with different initializations of the weights?
Oh, like, is it possible that we have a non-optimal solution? So the optimization problem is convex, so it shouldn't be a function of our initial guess. But certainly in other techniques, there will be such local optima.
Since fast charge is important for the auto industry, how applicable do you think the learned model would be to the highly dynamic aging experienced by electric vehicles, lab data versus real world?
Right. Yeah, I think that we would, of course, assume that in a real world context, there'd be a lot of other factors which would affect cycle life. I think that doesn't mean, though, that this isn't useful in and of itself, because it is enabling improved experimentation in the laboratory setting. So I can't say anything about how sure I am that this would generalize, but I do think that it has concrete applicability.
Okay, so it seems like we have covered all of the questions. I can see 31 questions in the Q&A box, and I think we covered all of them. Is that right, Mariam? Did I get all of them?
There's one more question now.
Okay, one more. Did you study the possibility of adding a third variable to the data set? What could happen if you did?
Third variable. I guess I'm not sure exactly what this question.
Maybe they're asking for like adding additional feature.
Yeah, I mean, certainly you could consider both different features or different measurement streams, and that could affect the result. It's hard to say exactly what the impact would be. I mean, we did see in our case where we only considered the variance of the capacity voltage feature relatively strong performance. but maybe, with additional features or some orthogonal type of measurement, you could do even better.
Great. So thank you so much for this great presentation. Is there anything you want to add before a wrap up? I know Mariam wants to add something, but is there anything you want to add before a wrap up?
No, thank you so much for having me. If people do have additional questions or want to check out other aspects of my work, I do have a website, or you could contact me. Again, it's kristen.severson@ibm.com.
Thank you so much.